gravity O and is in equilibrium with the weight P and Q. If a weight of 2P is added to P, the plank will be equilibrium again. This is what the question is saying. We have the plank of this length Rx. It is being pivoted at the center. We have one weight attached to this end, another weight attached to this end. We are not told that if we now had another weight of a value 2P, let's say for example, the weight we are having here is 10. We now have another weight of 2P, which is 2 times 10, which will be 20. So altogether it will be 30 here. And let's say what we are having here is just 10 or 20, which means the weight we are having toward this side is not bigger than this. Then this body will not be in equilibrium again. Then what are we going to do to keep this body in equilibrium? Let's have the option. Option A, moving Q nearer to O. That is, if we move this value of weight, we now move it nearer to this center, we need to keep the body in equilibrium. That's the option A, moving Q nearer to O. Let's look at option B, moving P nearer to O. That we should shift this one and move it to O, and we retain this one the way it is. We need to keep it in equilibrium. Then option C, adding a weight Q to Q. Option D, moving further away from center O. The best option, the answer to this question is option D, which says moving further away from O. By the time we have doubled this, all what we need to do is to move Q away. We move it away, a distance away from where we have the pivot. Before we begin to shift it, you shift it little by little, shift it little by little. Before you know it, it will keep this body in what? In equilibrium. Because it will balance the weight of this of this object, of this body. And the best option is option D. Question number 4. In the diagram above, the mass of the uniform metal rule is, we have the diagram here, we have a mass hang on this metal rule and another weight hang on this metal rule, which is 0.2 Newton, and we have the mass in gram. We have the mass in gram, in kilogram. Okay, the length from here to here is 40 centimeter. This is where we have the pivot. From this mass to the pivot is 10 centimeter, and from this the weight to the pivot is 30 centimeter. Altogether we have 40. So what will be the value of this mass? We have to calculate the mass. But in this case, I will calculate the mass, and I will still take the value of the mass to the, because what we are having here is weight. What we are having here is mass. Even though the question says you can also calculate the mass, I will calculate the mass, and I will also take this to the value of the weight as supposed to be here. Because if you look at the question, we are given the value of G to be equal to 10 meters per second squared. So we are still going to apply the principle of moments, clockwise, anti-clockwise. And the principle of moment says the clockwise moment should be equal to anti-clockwise moment. And that is how the question has been had from here to here. You can see you have been bringing it out. So let's see the approach to this question. We are going to have the mass times convert this centimeter to meter, 0.1 will be equal to the weight, 0.2 times 30, which is 0.3. So the mass will be equal to 0.2, 0.3 divided by 0.1. And if you try to analyze this, this is 0.6 divided by 0.1, 0.7 by 0.1. This is times 10 times 10. And if you try to take 0.6 times 10, you are going to have 60. That is 6 rather. Then this is 1, which is going to be 6 kilograms. So this is the mass of the mass we are going to have at this other side to keep this body in equilibrium. And the question says we should calculate the mass. The question says we should calculate the mass. This is the mass. But if you look at this, we are having the weight, not mass. This is weight in Newton. But what we are having here is mass. Even though the question says we should calculate mass, this is the mass. But let's take it to weight so that it will be uniform. The weight at this other side will be equal to mass times G. And we have calculated the mass, which is 6 times 10, which is going to be 60 Newton. So what we are supposed to have here should be 60 Newton. This is 1.2 Newton, this is 60 Newton. But if you are told to calculate the mass, this is the answer. But in weight, this is the answer. Let's take note of that. Question number 5. What is the value of X? You can see X in kilogram. What is the value of X in kilogram in the diagram above? This is the diagram we are dealing with now. We have a meter hood, or we can call it a hodge, or a lever, whatever may be the case. It is being pivoted at this point. We have two weights here, one weight here. And this is self-explanatory. From this point to this point is 1.5 meter. From X to pivot is 1.5 meter. From 15 kilogram to pivot is 2, because it has been shown. From here to here is 2, from here to here is 1. So it's very simple. You can just come around and say, we are still going to apply the principle of moment that say clockwise moment is equal to anti-clockwise moment. This is your clockwise, this is your anti-clockwise. For clockwise, we are dealing with two masses hang on this body. Let's take the first mass, X times half, okay, plus 15 times 2. That is for clockwise. Anti-clockwise, 50 times 1.5. Let's continue. This is X times 1 times 2 is 2, plus 1, 3 over 2, plus 50 times 2 is 30. This one is 50 times 3 over 2. Okay. This will give us 3x over 2 plus 30 will be equal to, let's try and call this 2 here 1, 2 here 25. Then we are having 25 times 3. And 25 times 3, 3x over 2 plus 30. 25 times 3 will give us 75. 75. Okay? So if we are to, we have 3x over 2 will be equal to 75 minus 30. And everything all together, if you take 75 from 30, we are having 45. Okay? From here now, that is 3x over 2 will be equal to 45. So that 3x will be equal to 45 times 2. Yes, over 1. This times this times this. Okay? So that 3x will be equal to 45 times 2 is what? 90. So that x will be equal to 90 divided by 3. 3 here, 1, 3 here, 3. So the mass we are going to have here now in kilogram will be 30 kilogram. This is equal to 30. 15, 30, 50. And that is the mass we are going to have at this site. Question number 6. Find the tension T1 in the diagram above if the system is in equilibrium. Tension is a force. We call it a tensional forces. And that is the type of force you can find in a string, in a hole, or in an elastic material. Okay? That is, we have to find T1. We have 3 forces, T1, T2, and then the weight, or the masses. These are the 3 forces acting at center 0. If we are to find the tensor T1, we are going to resolve this diagram into both horizontal components and vertical components. For horizontal components, consider the horizontal components. Let's join this together with this. This is horizontal. This is also horizontal. We can come around and say T1, okay, will be equal to T1 will be equal to, or let's resolve this first. Let's resolve this. Let's resolve